Problem 1950 is about RC circuits. They call them RC circuits because they've got a resistance and a capacitance. This is not the same thing as remote control, which is like RC cars. Alright, so if ever you have a resistance and a capacitance in a circuit with a voltage, then you use these ideas from Chapter 19 for the way the capacitor will charge or discharge and how that changes in time. Okay, it says that the total resistance R is equal to 15 times 10 to the 3 ohms, 15 kilo ohms. And the battery's EMF, it says, I never use that term. The voltage is equal to 24 volts. It says if the time constant, now time constant, when you hear that, you just write down R times C. It's one of the weirdest things about this section, that an ohm times a farad is equal to a second. I'll just write that here. Ohm times farad equals second. So 1 ohm farad equals 1 second. So the time constant, RC, is equal to 35 microseconds, which is 10 to the minus 6 seconds. Part A says, calculate the total capacitance of the circuit. Alright, well, we're given R and we're given RC, so we're supposed to find C. C is going to be 35 times 10 to minus 6 seconds divided by 15 times 10 to the 3 ohms. And a second divided by an ohm is going to be a farad, so I can write that. 35 divided by 15, this is 7 divided by 3. I don't know if you recognize this as 7 times 5 and this as 3 times 5. So 3 times 5, and this is 7 times 5. The 5s can cancel then, and you get 7 over 3. And you've got 10 to minus 6 divided by 10 to the 3, so you have 7/3 times 10 to the minus 9 farads. 7/3 is like 2.33 if you care. Probably not. Part B says, find the time it takes for the voltage across the resistor to reach 16 volts after the switch is closed. Does it tell us? It doesn't tell us whether the capacitors are full or charged, or sorry, fully charged or fully discharged. In this case, because it says that the resistance, the voltage across the resistor will ever get to 16 volts, we have to assume that the capacitors start uncharged. Let me show you how I came to that reasoning. If the capacitor is fully charged when you connect the switch, it's a really boring problem. All of the voltage will be dropped across the capacitor, and the resistor never has a voltage dropped across it, because if you remember, you can infer the voltage dropped across the resistor by looking at the current that flows through it and multiplying by the resistance. In this case, because the capacitor is fully charged, there is no current that would flow through the resistor, and so there would be no voltage dropped. It would always be 0. So we go back to, are the capacitors charged or not? They have to be fully discharged for this question to even make sense. Alright, so we start out with Q equals 0 coulombs on the capacitors, which means, if you remember, Q equals V times C. Now those are different C's. This is coulombs, like charge, and this is capacitance, like farads. I am so sorry. I don't know what to tell you. Okay. The point here is that the charge is proportional to the voltage. And so if these start charging because current flows through the resistor, then the voltage dropped across the capacitor will go up. At the beginning, there is no voltage dropped across it, and so all of the voltage, all 24 volts from the battery, are getting dropped across the resistor. All right. What was the question again? Oh yeah, the time it takes to reach 16 volts after the switch is closed. So let's look at V. This is V across the resistor, and it's going to start at 24 volts. And we're going to go down, 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 down like this. This is actually the kind of question I've already told you in the companion to the textbook. I'm not going to ask you this question, but let's do it just so that you can see it done. We want to know when will this cross 16 volts. The formula for this, the voltage across the resistor, is just E to the minus the time that it takes over RC, and then I forgot to multiply by V max, the initial voltage. Alright, we know RC, we know the VR and V naught, okay? I should just give you a preview. If I ask this question even on a future test, this would be like when we study radioactive decay, I would tell you the natural log of VR over V naught is equal to, and then I would give you a number. In this case, minus 0.405. I don't expect you to be able to know the values of natural log at random places. So I would give you the place that you need it. Alright, so let's solve this equation for time when VR equals 16 volts. 16 volts equals 24 volts. 24 volts times E to the minus T over RC, and I'll leave it like that, even though we know the value. I'll come back to it in just a minute. So we've got 16 volts divided by 24 volts, that's a 4, equals E to the minus T over RC. Let me bring this over here. So I've got the natural log of both sides will let me get rid of the E, 16 volts divided by 24 volts. Okay, the natural log of E to the something is just the something. So this is natural log of this, I told you, was minus 0.405, and that equals minus T over RC. Okay, the minus signs can cancel. And now I have T is equal to 0.405, so 40% of a time constant. A time constant would get you down to about 1/3 of the voltage. So about a half time constant gets you to 2/3 of the voltage, is what this is saying. Okay, RC is 35 times 10 to the minus 6. Let's see, let's call that, what, 40% of this. Half of it would be 17, and I just need to subtract 1/10 of it, so it would be 13.5 times 10 to minus 6 seconds. Okay, so 13 microseconds is how long it takes. Again, don't be scared by this stuff in green. I give you my word, I won't ask you quantitatively how this works. Qualitatively, I might say, what does the voltage look like as time goes by across one of these elements? But I'm not going to ask you anything where you need to solve for it, so you don't need to know this natural log business. We'll come to that later on in the class. I figure there's enough right now, enough new right now that you don't need that as well. Well, that's the end.